Hi, I'm Antonio Selle, and in this video we will discuss how to code in Matlab an interactive, more or less real-time animation of the simulation of a water tank. What we wish is to understand the code that responds to my keyword input, increasing or decreasing the inflow, and of course simulating the differential equation that empties the tank in a certain time, fills it. Again, it takes some time to fill it up to an equilibrium level in which inflow and outflow get equal, and how this input, the inlet flow, and output, the level, are plotted. So let's start explaining the code. We will use a Matlab class. What is a class? Well, okay, we can delve into the details of object-oriented programming, or just we may understand the class as a set of data, which is called properties in Matlab's language, which is shared among a set of functions that are called methods. So we have some function here, etc. And in this classdef, we just put everything together in a single Matlab file. Object-oriented programming has quite a few more subtleties, but we'll keep it easy with this interpretation of common data for a set of functions. A disclaimer is that the code we are going to explain is kind of simplistic, minimal and basic thing to get keyboard interaction, but Matlab has a so-called app designer, and that would be the way to go to craft a whole application with keyboard mouse interaction and beautiful user interface. But okay, this is a quick and dirty way of getting something to respond to your keyboard in order to create simple interactive animations, interactive simulations in this case. Let's go analyzing this main class. In these properties, we will store the last computed tank level, the last user set inflow value called U, simulation clock, and whether the simulation is running or not, so that the code that creates this object knows when to end. The first method we are going to discuss is the so-called constructor. This object has some shared data, but such data must be initialized somehow. And for instance, in this method I set the initial level to 1.5, initial input flow to 0, so the tank will quickly get empty, and the simulation clock, I'll start it with 0, and I'll set the simulation to running equal to. Now we will discuss the key aspect for keyboard interaction, which is getting a handle to the current figure, hfig, and setting for that figure the function to be called when a key is pressed. In Matlab code it has the name kpress function, and I will set that function to this one with this syntax. You can look Matlab's documentation of keypress function, but okay. The thing is that I will send the data for that keypress event to a method in my object called process kpress, which is that method. Well, here we have it. With this we get which key was actually pressed, and then, well, depending on which key was pressed, if it's the up or right arrow keys, I will increase the inflow in 0.1 units, or if it's the down or left arrows, I will decrease the inflow in 0.1 units. When I increase the inflow, if it reaches 1.5 or more, I will just cap it to 1.5 maximum inflow, and when I lower the inflow input, if it reaches below 0, I will just let it be 0 with this maximum code. And last, in this if I press the Q key, then I will tell whoever calls me that user told me to stop running. So the animation replies to my keyboard inputs interactively with this code. This is the important thing for the interactive stuff. Of course, as I said, the app designer has more flexible options. So there we have the constructor, and here we have the keyboard handling service routine. We will now discuss the core of the differential equation simulation, which will be the method that I called ODE step. What does this method do? Well, it just simulates that capital T seconds have elapsed, so it computes the next value for the level according to the differential equation model. So this is the differential equation. The time derivative of height is 1 over the tank section times the net flow, which is inflow minus outflow. So if we believe this model, then this part of the code carries out the Euler approximation in numerical integration textbooks. It says that the next value of height t seconds later will be approximately its first order Taylor series equal to the present value plus the time interval capital T times the derivative, the speed of level increase. So this is the so-called Euler integration, and what I do is just to avoid negative tank levels that would spoil the computations with square roots of negative stuff, and it's nonsense from a physical point of view. So if the tank level gets negative, I will just clip it to 0. Once I do the Euler approximation to compute the next level, I just increase the simulation clock by capital T seconds. So this is the core evaluation of the time response of the tank model as a differential equation. Of course, more accurate options, if capital T is not too small, can be done with ODE for 5 or a plethora of methods, but in here we'll just stick with the simplest one, which is the Euler approximation. So good. This is then the simulation. Once I have the tank levels, the only remaining thing is to draw the tank so that I get this beautiful figure. So let us now discuss the draw frame code, which I will draw 20 times per second later on. I will make it smaller, and I will now indicate which line of code draws which rectangle, because okay, everything is made of rectangles and text. So line 28 draws this greenish tank background. Line 30 draws this inlet pipe, and line 31 draws this inflow water falling from the pipe. The width of that rectangle is proportional to the inflow, so it gets thicker as inflow grows. Lines 34, 35, 36 draw this tank contour. Line 38 draws the outflow pipe. And line 40, as the important one, shows me the water level with a rectangle whose height is proportional to the actual tank height. So this is the main animation stuff. The goal of this simulation is understanding how tank level rises or lowers. So this is the line that does it. line 42 draws this red rectangle with some curvature argument so that it has rounded edges, and this rectangle for the slider is drawn by line 43, and all of these lines draw some text information here, here, here. All text in the figure is drawn by these lines 45 to 50. Just you can examine the code at will. Last, these two lines tell Matlab which region of the plane must be shown in the figure. These rectangles are the text were placed at given positions, and the axis line tells me which positions are shown in the figure, and I will make the actual axis not visible because this is not an ordinary function plot like those in the plot command of Matlab. So I don't want an ordinator and abscissa axis and grids, to be drawn anywhere in the figure. So when I finish all that, I tell draw now to refresh the frame, and this is the end of the code that draws a frame. So with this, we explained the class code, which is the keypress code, the simulation code, and the frame drawing code. Now we are in conditions to actually write some handling code for the simulation loop. In here, I create this object with the tank data and methods. I will tell it to simulate 200 seconds at 20 frames per second, so things must be updated every 1/20th of a second. This will be the number of samples, and this will be the data to be stored for the final figures. So this thing is the important simulation loop, in which basically I run the simulation for 1/20th of a second, I draw a frame, I store the inflow and tank level for later plots in figures, and I compute how long it took to simulate the differential equation and to draw the frame. Hopefully it's less than the sampling time, 1/20 seconds, otherwise I would have kind of overload and I will not be able to keep real time. If that does not happen, I will pause for one sampling period minus the time it took for the actual computations to keep roughly real time. Okay, this is not the recommended way for real-time interactive simulation. Video game programmers do things differently, but for an undergraduate student of basic Matlab and basic simulation, this is more than enough. If the keyboard handling code tells me that the simulation is no longer running, then I break out of the simulation loop, the for there, and I just, with these two plot commands, plot the input and output signals in my system. So this is the code. You can download it from my website, and then finally we can run it so the tank gets empty if no inflow gets in. The tank gets full until I reach equilibrium, or if I lower the inflow with my arrow keys in the keyboard, then it gets empty until a new equilibrium with less flow is reached. When I press Q, simulation ends, and I have these records for the input, red line, inlet flow, and the output, tank level, in blue. So this is it. We have explained the code for an interactive, keyboard-driven real-time simulation of a water tank, and we finish the video here. Thanks for watching.